This lesson's on 2D unconstrained optimization. And if you don't know what that word unconstrained is, don't worry about it too much for now. This is just meant to be in contrast to constrained optimization, which will be the subject of a future lesson. And let's start by saying something about the gradient vector. You may have seen the gradient vector in an earlier lesson, but in case you didn't or in case you don't recall, I'll remind you that for a function of two variables, f of x, y, the gradient vector is simply the vector of partial derivatives of that function. So here these subscripts x and y refer to partial derivatives. Partial derivative of f with respect to x and with respect to y. And of course that gradient vector can be evaluated at different points in the xy plane. That's what you may have seen before. I want to bring your attention to some key properties of the gradient vector that you might not have seen before. Okay, so these key properties that, first of all, the gradient points in the steepest uphill direction, where when I say the word uphill, I'm sort of using this analogy that a contour diagram or a function of two variables is sort of like a topographic map. So it points in the steepest uphill direction. And so what does that mean? You know, if I were interested in knowing the gradient right here at this point, this couldn't be the gradient vector, because if I take a step in that direction, I'm going uphill, I'm moving towards a higher valued contour than the one I started out on, but it's not the steepest direction. It's sort of like if you're walking along the side of a hill parallel to the flat ground rather than going straight up the hill. The steepest uphill direction would be going directly towards a higher contour, okay, something like this, okay? And very closely related to that is the fact that any gradient vector is perpendicular to the level curve on which it lies. So, you know, if we would like to ask about the gradient vector at this point, we know that it has to be perpendicular to this contour. And the way to imagine perpendicularity is first to imagine a tangent line to the contour. So there's a tangent line to the contour, and then you just go at 90 degrees from that. Okay, so that's the direction that the gradient vector will point. And I said that it points in the steepest uphill direction. I also want to comment that if you take the negative of the gradient vector, that's a vector that points in the exact opposite direction, and that's the steepest downhill direction. So the gradient, steepest uphill direction, negative gradient, steepest downhill direction, and they're both perpendicular to the level curve on which they originate. The other comment I'd like to make is that the steeper the ground is, the longer the gradient vector is. So thus far we've talked about the direction of the gradient vector, but the length of it means something. And since these are this gradient vector is composed of partial derivatives, and since you know partial derivatives measure something about the way or the rapidity with which a function is changing as you change one of the independent variables, the faster it changes or the more sensitive it is to the inputs, the bigger fx and fy are. The bigger fx and fy are, the longer this gradient vector is. And the way you assess this visually is by looking at the packing of the contour lines so long as the contour values are equally spaced, right? So like here, we've got to check that these contours are all the same distance apart in terms of the function value. Like this is -2, -1.5, -1, so it's increasing by 0.5 on each contour that's shown. I changed that here. There's a 0.2 contour here, but the rest of them differ by 0.5. And so what you can see is that, you know, the distance you have to travel to get, say, from -2 to -1 up here is much further than the distance you have to travel to get from -2 to -1 down here. These contour lines are close together. These same contours are further apart here, okay? Since these are closer together, that means that the function is changing more rapidly. It's steeper, right? It's a steeper hill. If you walk the same distance, your elevation increases more here than it does here. And that means that here, the gradient vector should be relatively long, and in comparison, the gradient vector here should be short. Now, you've learned previously what critical points for a function of one variable are. They're just places where the first derivative equals 0. Analogously, critical points of a function of two variables are places where the gradient vector equals 0, 0. Or another way of saying that is each partial derivative. So you can remember that the gradient vector means f sub x, comma, f sub y. So this is just a way of saying that f sub x equals 0 and f sub y equals 0 for it to be a critical point. And there are different kinds of critical points you can have in functions of two variables. The ones that are going to be most familiar to you are things like maxima and minima. So I'm showing you those in this sample contour diagram here. You see some kind of circular contours. These are increasing in value. So you imagine that somewhere in the middle here, there's a point where the gradient equals 0. And from looking at the contours, this turns out to be a local maximum. Okay. On the other hand, this one, there's a point in the middle here where the gradient vector must equal 0. And since these contour values are going down as you move in, this is like a valley. So this is a local min in here. There's another kind of sort of famous critical point you might encounter in 2D, and that's called a saddle point. So it's interesting to contrast this to a hill or a valley, right? If you're at the bottom of a valley, it means no matter what direction you go in, here's the bottom of the valley, no matter what direction you go in, you end up going up as you walk away from that point, okay? A saddle is different. A saddle is essentially a minimum in one direction, but a maximum in the other direction. So if I were an ant walking along this surface and I was walking this way, then this red point here I would perceive as a minimum, right? It would be my lowest point on that path. On the other hand, if I were walking this path, I would perceive that point as the highest point. And this kind of point is called a saddle point, for the obvious reason that this surface on which it occurs is shaped like a saddle. So in practice, we can ask about, what do we do with critical points and optimization for functions of two variables? And there are a few ways to proceed. You can seek the critical points, and we know the test for that. We've already said it's that the gradient vector should equal 0, 0. And then there are some analytical tests you can use to classify that point. So there's kind of mathematical formulas you can use to determine whether your point is a maximum or a minimum or a saddle point, similar to the way that for functions of a single variable, you learned the first derivative test or the second derivative test. Now, you'll learn those for functions of one variable in this course. We're not going to learn those tests for functions of two variables. It's the kind of thing you would learn in a standard multivariable calculus course, but we're not going to do it here. Something that you can do is just plug in numerically or make a graph, right? Like test points nearby your critical point to determine whether you think your critical point is a minimum, a maximum, or neither. A different approach you could take is to perform gradient ascent or descent. And in a previous lesson, you've seen this idea for functions of a single variable. There's another lesson where we'll use some software, RStudio, to perform gradient ascent or gradient descent on functions. So you won't see that in this screencast here, but that will come in a later screencast. For now, I just want to do a quick example of where we seek the critical points and then test nearby points to classify the critical point. So let's take as an example the function of two variables written down here. And to seek critical points, we compute the gradient vector. So if I differentiate with respect to x, I get 2x plus 6. That's 2x plus 6 here. And then I differentiate with respect to y, and I get 2y minus 10. That's 2y minus 10 here. And if I would like to know where that gradient vector equals 0, 0, it's easy to solve here. It's x equals minus 3, y equals 5. So there's only one critical point. And then if I want to assess what sort of critical point that is, I've just made a quick quick table of values here. So in the center, I have the value of the function at the critical point. It turns out to be minus 26. And then I've made a grid of values of what happens if you step a little bit to the right, a little bit to the left, a little bit backwards, or a little bit forwards. And you can see that since the function value at all those close by points is slightly greater than the function value at the critical point, we conclude that this is a local minimum. That's it for this lesson. I want you to reflect and ask yourself if you can state the key properties of the gradient vector and even apply them on a contour diagram, if you can locate critical points of functions of two variables, and if you can classify them. Thanks for listening.